Hello and welcome. Have you ever really stopped to think about what happens when you type a web address into your browser and hit enter? It feels like magic, but it's really not. It's actually this incredibly well-organized dance between rules and code. And in this explainer, we're going to pull back that curtain. We're going to start with the fundamental rules that run the entire internet and follow them all the way down to the actual lines of code that bring network applications to life.
So, here's our game plan. We'll kick things off with the basic protocols, the absolute foundation. Then, we'll see how these protocols are smart enough to avoid creating massive digital traffic jams. From there, we'll dive into the programmer's toolbox with sockets, look at some really important server design choices, and then wrap it all up by applying these ideas to solve some real problems.
All right, first up, protocols. The best way to think about these is as the internet's universal language. They're the shared set of rules, kind of like grammar and etiquette, that lets a server in Tokyo have a perfectly normal conversation with a laptop in Toronto. And right at the heart of all this, there are two names you'll hear over and over again, TCP and UDP.
This image here really nails a huge design choice that every single networking app has to make. See, on one side, you've got stuff like web browsing or downloading a file. For these, getting the data exactly right is everything. I mean, you can't have a web page show up with missing chunks, right? That's why they use TCP. It's all about reliability. But then on the other side, you've got something like a voice call over the internet. In a live chat, if a little piece of audio gets delayed, it's totally useless by the time it arrives. It's actually better to just drop it and keep the conversation flowing. Speed is way more important than perfection. And for that, you use the much faster UDP.
This really brings us to the central trade-off. TCP is like sending a registered letter. It's all about guarantees. Before it sends a single byte of data, it does this thing called a three-way handshake, which is basically a quick, "You there? Yep, I'm here. Okay, great. Conversation." It numbers every single packet so they can be put back in the right order, and it waits for a confirmation for every piece it sends. If something gets lost, it just sends it again. Now, UDP, that's your postcard. You slap an address on it, drop it in the mail, and just hope it gets there. There's no setup, no confirmation, nothing. It's a fire and forget system, which makes it super, super fast.
And here is the perfect real-world example of that choice in action. DNS is basically the internet's phone book. It turns names we can read, like Google.com, into IP addresses computers can read. And this happens billions of times a day. Can you just imagine if every single one of those tiny little lookups needed the whole formal ceremony of a TCP connection? The entire web would feel like it was crawling through mud. So because these requests are small and speed is everything, UDP is the perfect tool for the job. If a request gets lost, no big deal. The computer just asks again. It's still faster.
Now, because TCP is the reliable workhorse carrying most of our important traffic, it has a massive responsibility. It has to be a good citizen on the network. I mean, if every single computer just blasted out data as fast as it possibly could, the internet would collapse in seconds. To stop this from happening, TCP has this really clever built-in system to sense traffic jams and slow down. We call it congestion control.
Okay, so the main tool for this is something called the congestion window, or CWnd for short. Just think of it as a dynamic speed limit. It's the sender's best guess about how much data it can have in flight, sent but not yet confirmed, without clogging up the pipes. If all the data is getting through smoothly, TCP thinks, okay, the road is clear, and it might raise that speed limit a little. But if those confirmations stop coming back, it slams on the brakes, assuming there's a traffic jam ahead.
But here's the thing. The network itself isn't the only place a bottleneck can happen. The computer on the receiving end has a limited amount of memory, a buffer, to store incoming data. So the receiver window, or RWend, is just the receiver's way of telling the sender how much space it has left. With every confirmation it sends back, it's basically shouting, "Hey, my inbox is getting full. I only have this much space left, so don't send more than that."
So this all boils down to a very simple but really elegant rule. Every TCP sender has two speed limits it has to watch: the network's limit, CWnd, and the receiver's limit, RWend. And to make sure it doesn't cause any problems, it always has to obey the slower of the two. The actual amount of data it's allowed to send is the minimum of those two windows. It's a brilliant way to make sure it doesn't overwhelm the network or the computer at the other end.
So how does TCP actually adjust that network speed limit? Well, it uses a clever little algorithm called AIMD. That stands for Additive Increase, Multiplicative Decrease. The logic is a lot like driving in traffic. As long as things are going smoothly, you gently and additively increase your speed. You're just tapping the accelerator. But the very second you see brake lights ahead, which for TCP is a lost packet, you don't just ease off the gas, you slam on the brakes and multiplicatively decrease your speed, cutting it in half.
This cautious but quick-to-react approach is one of the key things that keeps the internet stable.
Okay, so we've got the rules of the road down. We understand TCP and UDP, and we know how TCP avoids creating traffic jams. But how do we, as programmers, actually get behind the wheel? How does our code physically open a connection and start sending data? Well, the answer is a standard toolkit that you'll find in almost every operating system, the Sockets API.
Now, I know this diagram might look a little complicated at first, but trust me, this is the fundamental blueprint for almost all network communication. Over on the right, you've got the client steps, which are actually pretty simple. It just creates an endpoint, a socket, and then tries to connect to a server. The server, over on the left, has a bit more work to do. It has to get itself ready to just sit there and listen for connections from anyone. So let's walk through what the server has to do.
Let's use a phone analogy here. First, the socket call is like getting a brand new phone from the store. It's just a device, it doesn't have a number yet. Then, bind is you going to the phone company and saying, okay, I want this specific public phone number for this phone. This is your IP address and port. Next, listen is basically turning the ringer on and telling the network, hey, I'm open for business. Go ahead and start queuing up calls for me. And finally, accept is the part where you actually pick up the ringing phone. Your program will literally pause or block right there until a client connects. And here's the really cool part. When a client does connect, accept gives you a brand new socket just for that one conversation, which leaves your original listening socket totally free to hear other calls coming in.
So, that accept call brings up a really critical question. If your server is busy talking to one client, what happens to everybody else who's trying to connect? They just get a busy signal, right? Well, a server that can only talk to one person at a time isn't going to be very useful. And this leads us to a fundamental fork in the road for server design.
On the left, you see the problem, a huge bottleneck. If a server handles clients one by one, we call that an iterative server. A much better way to do it is the concurrent server on the right. And how this works is so clever. The main server process, its only job is to listen for new calls. As soon as it accepts a connection, it immediately uses a system call called fork, and fork literally creates a clone of the server process, a child. This child inherits the connection, and its only job is to talk to that one client. Meanwhile, the original parent process is instantly free to go back to listening for the next connection. It's a beautiful way to handle many clients at once.
And this brings us back to another one of those classic engineering trade-offs. An iterative server is like a single-lane country road. It's super simple to build and understand. The code just runs top to bottom. But, if you get stuck behind one slow client, everybody else is stuck in a traffic jam behind them. A concurrent server, on the other hand, is like a massive, multi-lane highway. It's way more complex to design. You have to worry about all these different processes running at once, but wow, can it handle a ton of traffic. For any real-world application, concurrency is really the only way to go.
Okay, we have covered a ton of ground here, from high-level rules all the way down to nitty-gritty server code. So now, let's make this all concrete. Let's take what we've learned and apply it to a few questions to really see these principles in action.
All right, first question. We know a TCP sender has to deal with two different speed limits, right? The network's capacity, which is the congestion window, and the receiver's buffer, the receiver window. So how does it decide how much data it can actually send? Does it pick the fastest one, the slowest one?
And the answer is D, the minimum of the two. This makes perfect sense when you think about it. If the network can handle 100 packets, but the receiver can only handle 10, what happens if you send 100? You're just going to crash the receiver. So to be safe, the sender always has to obey the tightest restriction. It has to go at the speed of the slowest part of the system.
Okay, next up, server design. We've just talked about how much better and more scalable concurrent servers are. So why on earth would anyone ever choose to build an iterative server? What's its one big selling point?
The answer is B. It is just plain easier to build and debug. Going concurrent is powerful, but it opens up a whole new can of worms. Really tricky bugs that are a nightmare to track down. An iterative server's logic is totally straightforward. Do this, then do that. For simple tools, or even just for learning, that simplicity is a massive advantage.
And for our last question, let's zoom back in on that server setup sequence. We have those key functions: bind, listen, and accept. What is the specific one and only job of the listening function in that chain? That's right, the answer is B. It puts the socket into a passive listening mode. Let's go back to that phone analogy one last time. Binding gives the phone its number. Accept is what actually answers a ringing call. Listening is that crucial step in the middle. It's the command that tells the operating system, hey, I'm open for business now, start watching this number for me, and queue up any incoming calls. It's what officially flips the open sign on for your server.
And there you have it. We've gone on the full journey, all the way from a high-level theory like TCP congestion control down to the actual listen and fork calls you would type into your code. This blueprint, this is what powers pretty much everything you do online, from web servers to video games. And now you have the foundation to understand how it all works. So the only real question left is, what are you going to build with it? Thanks for watching.